I'd like to introduce Aavik Wadivkar. He's a undergraduate student at Washington University studying astrophysics and philosophy. While his research focuses on exoplanetary work with TESS, he can explain what these acronyms are, not me, and the Habitable Worlds Observatory. He also serves as president of WashU Satellite, a 50-plus person undergraduate engineering team that designs and builds space-ready science missions. He is presenting today on AIRIS, another good acronym, he'll explain that. One of the missions flying on NASA's high-altitude balloon mission in Antarctica this year. I will give a little hint. I did see a presentation about 3 months ago. I went down to Astronomy on Tap because I wanted to talk to that group about potentially coming to the MSRAL convention. And he was one of the speakers there. And I was talking to him later on, actually at another event, that I was recruiting him to speak for tonight. And I said, this is really great. I mean, you graduate students, you get to do some pretty neat stuff. We never got to do this when I was, in graduate school. He goes, Don, this is all undergraduate work. I'm like, God, so you kidding. When I was in school, we didn't do anything even close to this. We were doing statics. That was about it. So with that, turn it over to Aavik.
Okay, thank you. Can people hear me? Is this thing on? Yay, can people hear me? Okay. Yes, how does this sound?
A little higher. Good.
A little higher?
Just a little higher, yeah.
Okay, hold on. Technical difficulties. All right, how about this? Okay, perfect. Well, hello everyone. Thanks for having me. And Don, I gotta say, we are still doing statics. So no worries, things haven't changed that much. But it's great to be here. As he mentioned, my name is Aavik Wadivkar. I'm an undergrad at WashU. I'm studying astrophysics and philosophy. I'm here because I'm also president of WashU Satellite, which is an undergrad team that works on satellites and space missions. As you mentioned, I also work on exoplanetary research, kind of on the side, with TESS, which is the Transiting Exoplanet Sky Survey, or Survey Satellite. I forget which one it is. And I hope my professor doesn't get mad at me for that. But I've been working with TESS for about 2 years on transiting exoplanets, and this summer I'm currently working at NASA, all over in DC, working on the Habitable Worlds Observatory, which is going to be NASA's next flagship mission, and it's designed to look for, characterize, and hopefully find life on habitable worlds outside of our solar system. But that's not what I'm here to talk to you about today. I'm happy to take those kinds of questions during the Q&A. Here I'd like to talk about AIRIS. However, first I want to just give a quick hand to Dawn and Ellen Ladwig for putting this thing together. This has been a phenomenal day. So thank you guys so much. Thank you, of course, for having me. They offered to fly me out here because obviously I was all the way in DC. They offered to have me stay at their place. Just in case, well, he said, you're allowed to stay at my place, but only if you give me a couple compliments during the thing. So, I had to say something. But no, he and Ellen have been amazing hosts. They've been fantastic at putting this whole thing together. I'm very thankful for them giving me the opportunity to speak here. And so, okay, without further ado, I think it's worth getting started. So, just to be clear about our agenda for today, first, I go over a little bit about WashU Satellite, who we are, what we do, why we do what we do. I'll go over a little bit about GRBs, the science background and the motivation for our mission. I'll talk about balloon missions first and foremost, which kind of sets the stage for what we're working on, and then finally get to, yes,
You've got some problem with the feedback.
Oh, this is, okay. More technical problems.
Yeah.
Can people hear me if I shout?
No.
Okay.
Does it?
Better?
Just away from that live mic, I think.
Okay, can people hear me?
Yes.
All right, perfect. Yeah, so I'm going to talk about AIRIS finally, which is the actual mission that we've been working on for the better part of 2 years. And then I'll end with our current progress and lessons learned, and then what the future of WashU Satellite looks like. So first and foremost, who are we? As you may have noticed, we're WashU Satellite. We are an engineering team, a design engineering team at WashU. We work on satellites and space technology. We were founded just about 2 years ago, and so we're a very young team. WashU has a handful of other design teams, like a racing team, like a rocketry team, etc. However, they do racing and model rocketry. We work on satellites. We work on space technology. Since we are fairly new, we're still Trying to hit the ground running, of course, and AIRIS is one of our very first missions. We have another going on at the same time, which I'm happy to talk about later. We are about 60 members strong, give or take, based on where we are in our recruiting cycle. And as we are an engineering team, we are primarily made of, you guessed it, engineers. So this means mechanical, this means electrical, this means software. At the same time, we also have people from systems engineering, which is a little rare to see, especially at the undergrad level. We have our mission ops team, which are designed to keep missions running, keep constant communication with them, and so they have more of a bit of a holistic role. We have the physics team, which is what I was part of when I joined, because of course I do physics, I'm not an engineer. And I joke that the physicists are kind of the consultants of the group, because we figure out what the group needs, we figure out how to design things, and then we just tell the engineers what to do. We don't worry about anything else, and then they get mad at us. And then of course, finally, we have our business and outreach team, because space is, it's getting cheaper, it is still kind of expensive, and someone has to keep the lights on. And of course, we are all, as Don so greatly mentioned, we are undergraduate led. I'm an undergrad, most of the team are full of undergrads. We do have a few master's degrees, dual degrees, that kind of thing. We're primarily undergrad led, although we do have a lot of collaborations with grad students and professors and actual graduate level research. So now, the value proposition, aka, why do we exist? What's the point of this? So, on one hand, you have people like this professor, or scientists. You have people like Dr. Jim Buckley, who works at WashU, he's a professor, and he works on plenty of missions over the years, plenty of proposals, and Professor Buckley has some great stuff. He has institutional ethos. He has trust. He has builds trust in the community. He can write a proposal, and people at NASA will know his name. Because of that, he might even get money for it. However, he doesn't have the time or bandwidth necessarily to have really fun, extended engineering projects, and so it's hard to execute at scale. Right? On the other hand, you have us. We're engineering students. We have no money. We have no institutional ethos. NASA does not know our names. But we do have plenty of time on our hands, despite what my people during finals week will tell you. We have plenty of time, and so at the same time, just time doesn't get us to space. However, the idea is that collaboration with engineers and academics, with researchers, with people with this institutional ethos and financial backing, financial support, we're actually able to fully execute missions at scale. Things that help both them and us, people that help missions that help extend their research while not eating into their time, and things that help us get experience in engineering and experience hands-on for hopefully industry, academia, whatever our members would like to pursue. So now let's move into the science background for AIRIS, aka why what we're doing matters. And I'll get to what AIRIS is, and I'll get to what it stands for in a bit. Don't be spoilers. But for now, you have to know that AIRIS is the name of the mission I'm talking about, and that's all I'm going to tell you right now. So I have to tell you a brief story. To be frank, AIRIS does gamma ray astronomy, and at every single gamma ray lecture, especially public lectures, a single story is told. And it is like the single story, and you have to hear it, I have to tell it, so now it's finally my turn. This is the Vela satellite. The US launched a good handful of those around the 1960s, and you may be asking why, and if you guessed it was because of the Cold War, you'd be right. It's because at the time we had signed people were scared that, the Soviet Union, the US, countries are going to start testing the nuclear bombs in places that are not so great to test because, we live there. And so they said, okay, no testing in underwater, no testing in the atmosphere, no testing in other certain places. And so it was called the Partial Nuclear Treaty Ban. I forget, PTBN, PB, NT, I forget the end. But the idea was that it would ban these. This kind of testing. The US obviously did not trust the Soviet Union for whatever reason. Who knows? And so the US decided, okay, we're going to launch satellites, and we're going to look for evidence of any nuclear bomb testing to make sure, right? Trust, but verify. And so they launched these Vela satellites, and these Vela satellites were designed to pick up the residue from nuclear bomb explosions in the upper atmosphere. And around, a couple of years into the first Vela satellite, they picked up a blast, but it didn't look like a nuclear blast. It was kind of weird. They weren't sure where it came from, and it didn't look like a nuclear blast would. So they thought, okay, instrument failure, something's weird going on, whatever. We're not going to make a big deal of it. And then they found another one. And then they found another one, and before long, they found a ton of these blasts all over. And they thought, okay, something strange is going on, right? We've never seen these kinds of blasts before. They don't look at all like nuclear blasts. We're fairly certain it's not, the Soviets, because then our entire atmosphere would be irradiated. So something strange is going on, something weird, something that we haven't explained yet. And so eventually, after this mission was kind of declassified and they decided, okay, we can't release these things, they released a paper on it. I think this was around the 70s, or sorry, 67, on gamma ray bursts of cosmic origin. They ruled out it did not come from the Earth, it did not come from the Sun, so it's cosmic origin. And in terms of what these actually look like. First, I have to make sure that we're all on the same page with what we're talking about. This is a visual spectrum. You guys are amateur astronomers, you're very familiar with this. But just in case we're not, visual spectrum is the electromagnetic spectrum that light falls on. For visible light spans from the long wavelengths to the short wavelengths, from red all the way up to blue. Of course, you may also know that the visual spectrum is just a tiny part in the wider electromagnetic spectrum. Over here we have the wonders of C-SPAN, we have radar, we have thermal cameras, we have sunburns, we have doctor's appointments, and we have nuclear bombs and the Incredible Hulk. And of course, the visible light spectrum is just right there sandwiched in the middle. And so when we're talking about gamma ray bursts, we are talking about these little pieces. And when I say bursts, I mean literally just bursts. Astronomers are fantastic at naming things, you'll come to notice. And so when they say gamma ray bursts, they meant it was just a bunch of photons that happen to be really high energy that we call gamma rays. So we see a bunch of these, right? We eventually decide to launch a mission to figure out, okay, where exactly did this come from? And we launch a mission with the capability to localize exactly where they're coming from in the sky. And it's called the BATSI mission. It's the Burst and Transient Space Experiment, I believe. And so you can see, things are scattered all over. The bottom is the power. Can you see the pattern in this mess? Yes, no, no. A lot of people are saying no. Okay, great. Me neither. Right? And in fact, not a good day. Right? No one could see any pattern to this, and that was kind of strange because usually when we expect certain things to be constrained to areas, right? For instance, asteroids, comets are by and large, constrained to the elliptical, the line in our sky that dictates where all the planets follow, and the sun is it's a place where everything orbits. It's a plane that everything orbits the sun. Similarly, if we're talking about things in the galaxy, most likely we're talking about things that exist on the galactic plane. That makes sense. The stars are there, the nebulae are there, everything that exists in our galaxy is by and large centered in there. But of course, these gamma rays are not distributed like we'd expect something within our galaxy to be. And so this was our first clue that, okay, not only are these strange, they might not even be part of our galaxy. And we're just coming off, this is a couple decades after Hubble discovered that our galaxy wasn't the universe. And so we're kind of reading, okay, what exactly are these things? Not only are they pretty bright, pretty energetic, because you've got to have something super energetic to produce these gamma rays, they are not even in our galaxy. Okay, so finally, we tracked down exactly how far away these are. This was in 97, it is 97508, and we finally calculated its distance using its redshift. And what we found is that this thing was 6 billion light years away. And if you're like me, you have no idea what that means, right? Because astronomy is full of long numbers, billions and millions and trillions, and they all have blurred together. But to give a sense of scale, the Andromeda Galaxy, which is our closest major galactic neighbor, not including the Magellanic Clouds or anything, is about 2.5 million light years away. Okay, so that entire galaxy is 2,000 times closer than whatever the hell is causing this burst. It is so ridiculously far away from us, right? And because of the inverse square law, that has to do with the thing that reduces the amount of light that's on how far it is, that means that, okay, dimness, brightness scales with distance, and so if this thing is 2,000 times farther away, it also has to be 4 million times dimmer, or it should be. But we're still picking it up, which is pretty weird. And so they finally measured its energy based on its distance, because that's something you can do. You can measure how much energy you receive from it, and then based on its distance, figure out, okay, how much energy must it be producing at the source. And before I tell you the number, again, I gotta give you some orders of scale. So first, we're gonna only talk about powers of 10, do some high school math, basic stuff. For astronomers, we don't need to worry about anything other than orders of magnitude. So our sun produces about 10 to the 26 joules. That should be joules per second. My physics teacher is pretty mad at me. We're going to do back of the envelope, say that there are about 100 billion stars in the Milky Way, assume every one of them is like our sun. Okay, we're getting that our galaxy produces is, add those two together, we get 10 to the 37. Okay, 10 to the 37 joules per second. This burst, which lasted on the order of seconds, produced 10 to the 43 joules. And that is ridiculous. That means it is a million times brighter than our galaxy, and every single star in our galaxy combined. And it expanded all of that energy in just a few seconds. And so now we're thinking, oh, something really weird is going on, right? Not only are these very energetic particles, they're extremely far away from the galaxy, and they're created in these like cataclysmic events, right? Thank God these things aren't near us. And so we eventually collect more data, and we finally discover that, okay, it seems like there are two types of these events. There are pretty short ones that happen under 2 seconds, and then there are kind of longer ones that happen over 2 seconds. And so astronomers did what they do best and named them long bursts and short bursts. Fantastic. And it turned like they were about 30% short bursts, 70% long bursts. And so because these things seem so characteristically different, people wondered, are they caused by maybe different mechanisms? Because by and large, when we're talking about short events versus long events, just in terms of causality, right? It takes so long for light to travel, it takes so long for things to cause one another. And so the idea is that if you see a very short event, it was likely caused by a pretty compact source. If you see a very long event, it was likely caused by a fairly extended source. And so that's what we had to go on with. Now, in terms of our current theories, we have a couple floating around that are generally well considered. The problem is that, of course, we are detecting them we're looking at these from all the way over here, on the other side of the universe, which on one hand is a blessing, right? Because if we were closer, then it's like having a Death Star pointed at your face. Not ideal, right? We probably wouldn't be here to talk about it. In fact, there's some evidence that people have that earlier extinction events were actually caused by gamma rays being unfortunately aimed at Earth. But we should be grateful that they haven't been stronger and closer, or there might not be an Earth to talk about. Now, our current theory for especially the longer bursts, things called collapsars, which I was disappointed to learn is not the name of a Muse album, which is the same, I love Muse. But no, collapsars is a type of very exotic star, in particular a way that a star dies. So first, gotta cut a star open and talk about this. Don't worry, we'll put it back together. Inside a star, it's layered like onions, it gets hotter, it gets more pressurized until you get to the core in the middle. And every star, just some straightforward stellar astrophysics, every star is an arm wrestle. It's a wrestling match between the core, which pushes outward with nuclear fusion and supports the star and supports all its energy and output, and gravity, which inevitably tries to push things together. And so, for billions of years, these two have a tug of war until, spoiler alert, gravity wins. In particular, we run out of fuel. In collapsars, the core transforms directly into a black hole. And it turns out that if the star is massive enough, if the conditions are right, the core can collapse directly into a black hole without the outer layers having time to shed. And then the black hole immediately gets on to feeding on the rest of the star. And so that black hole engine is what we imagine causes these long gamma ray bursts. And so there's still a lot that we don't understand about them, right? There seems to be that a lot of these gamma ray bursts are followed by what we call afterglows, which have other kinds of wavelengths going on. It has X-ray, it has UV, it has optical, all the way down to radio. And we generally understand why that is. It's because of something called synchrotron radiation. But regardless, the way that these are shaped and characterized are still not completely understood. There's some gamma ray bursts that are 7 hours long. But the idea is that the long ones are caused by this collapse. The short ones are probably caused by neutron stars colliding with one another, which we're pretty sure is the case because we saw 2 neutron stars collide with each other with gravitational wave observing, and then saw the gamma ray bursts, and we're like, okay, 1 and 1 makes 2. But that being said, there's still a lot that we don't fully understand about these objects. So now I'm going to make a hard and fast segue. I got to talk a little bit about balloon missions and why they're so important to constraining these gamma ray observatories. So first, unfortunately, if you've ever observed on Earth, you'll notice that while we do great with visual light, it's very visible light is visible on Earth's surface. It's funny how that works. And while we're great with certain kinds of radio waves, we're kind of out of luck when it comes to anything higher, so like UV and higher, and a lot of IR, which is why telescopes like James Webb, or telescopes like Roman, or future telescopes like the habitable worlds observatory have to be in space because Earth's atmosphere blocks a lot of things. In particular for us, it blocks gamma rays. And so that's why the only time we found gamma rays was when we sent a satellite up out of Earth's atmosphere. And so, what's easier than getting to space is getting almost to space. What's cheaper than getting to space is getting almost to space. And so, NASA has balloon missions. These are huge helium balloons that carry payloads up until the upper atmosphere and then hang them there for about a month, and then the balloon pops and they come back down. Now, usually when then do a little telescope on top of it that does your observing. Usually when people think balloons, helium balloons, we're thinking party balloons. I gotta tell you, this is not the case. This is a balloon, and that is the Washington Monument for scale, if that helps. If that doesn't help, here's a car sticker advertisement. You can fit 200 billiard rings in one of these, and a football field. So these are enormous balloons, and the reason that it looks like this at launch and this up there is the atmosphere is thinner, so there's more internal pressure, puffs it all the way out. But these things are monsters, because they have to be if they're launching effectively payloads weigh about as much as a car, all the way up into the upper stratosphere. But it's cheaper than a rocket. Now we come to, in particular, this ADAPT mission. So the professor that I mentioned, alluded to at the beginning, Professor James Buckley, works on the ADAPT collaboration. In particular, ADAPT is this demonstrator for future technologies to find gamma ray bursts. There hopefully will be a telescope someday in the future around L2-ish, looking for gamma ray bursts, but first to prove that the tech works, because they're trying more advanced tech to help localize things better, they're thinking, okay, let's demonstrate it in Antarctica. So this telescope is called the AET, so they made the Antarctic demonstrator for the AET, or ADAPT. I know, it's straightforward, right? And so they're working on they decided to make the detector, hook it up to the balloon, float it up there. In terms of how the detector works, because gamma rays are strange. You can't observe them with CMOS. They'll burn through, they'll leave a hot pixel. You can't observe them with most ordinary ordinary methods. So you have to use something called Compton scattering. And I was going to not include this because it's physics that we don't strictly need. However, it so happens that Arthur Compton discovered Compton scattering at my hopefully alma mater, WashU. And he actually taught at WashU. He was department head at WashU, and he was chancellor after World War II. And so, of course, I do have to talk about Compton scattering because I have to talk a little bit of WashU history. So we discovered that there are certain relationships between how photons scatter with electrons, and the angle that it scatters at, and the outcoming energies from that event. And the details aren't important. The math isn't important. What is important is it was cool enough to give him the Nobel Prize. And so it was a pretty important discovery. There's actually a plaque of it at WashU. Funnily enough, where he did the experiment is not where the physics building is now. It is in the English building. So maybe he needed the news to figure it out. I'm not sure. But regardless, we can use this to try and reconstruct where gamma rays come from. And the way we do it is, we have two different layers of detectors. Our gamma ray comes in, it scatters off the first one, it collides into the second. Based on the relative energies, we can figure, okay, it must have come with a certain angle from this initial, you connect a line between the two, right? There must have been some angle of scattering, but it exists somewhere on this circle in the sky. And if there are enough photons, then all these circles, there are different circles, and they all overlap, hopefully, where we estimate the gamma source to be. And so this is the basics of how ADAPT works. And that's why ADAPT works like a stack of pancakes, because it is all detectors all the way down. So gamma ray bursts will come in, ping pong between them, and then we can hopefully work backwards a little bit. So we attach it to a balloon, we send it up to Antarctica, where it floats around in the polar vortex for about a month, and then pops and comes down to Earth. Okay, now, I will say there's a piece of this that would be super helpful to know, and that's in particular the optical counterpart of these gamma ray bursts. Like I mentioned, right, gamma ray bursts are gamma, so that's why you can't have normal detectors, but they also sometimes come with optical counterparts, right? And so something that you can actually see pop in and out on the sky. Now the problem is it's hard to constrain this because an optical telescope needs to be looking at the right place at the right time, and that's hard to do, or it needs to be super fast to respond. But the thing is, there's a pretty strict need for this because it helps with a lot of things. It helps with our localization efforts because gamma ray bursts or gamma ray detectors can only get so localized on the sky. It helps with constraining a lot, that helps with follow-up observatories, telling them where a point, when you tell an astronomer, oh, it's in that general 20-degree section of the sky, they'll tell you to go pick rocks and waste someone else's time. It helps with early light curve measurements, which you can detect morphology and evolution of these, and it also helps with kind of constraining some of the early the physics that we don't strictly understand about these. And it's a lot of complicated things that I don't fully understand. But the takeaway is that if we have an optical counterpart, then we have the when, we have the where, and we have the how. It really helps us with constraining these gamma curves. Okay, so finally, with all that build up, we come to AIRIS, which is what WashU Satellite has been working with. So first, what is AIRIS? Well, it is the Adapt Incidence, what is it? The Resolution and Imaging Subsystem. We made the acronym before we made what it means. It's AIRIS standard. And yes, we put an acronym in our acronym because we're feeling cool that day. But okay, what is AIRIS actually? It's just a telescope, right, effectively. It's a fast-moving optical telescope designed to follow up on these gamma rivers. And we have a certain mission statement, gamma ray localization, light curve morphology, whatever. The point is that it points and looks at gamma rivers after ADAPT sees them, so we can basically measure what they look like in the optical band. As I mentioned, we do expect visible light to show up at some point in the picture. And strictly speaking, a lot of papers have come out where we're still not 100% sure where this emission comes from. We know that some of it comes from this thing called synchrotron radiation, but some of that's not always the case. So there's a lot of new science that could potentially be made. This is where it actually looks like. So finally, you guys get a picture of what I'm talking about. And it is a box with a lens on it, right? So this is the lens, this is the sensor back here, this is the box housing all of the electronics. In particular, the lens is a commercial off itself. It's a Canon 200mm, pretty fast lens, 1.8, and pretty wide field of view. And we also have a red filter because it is day all the time in Antarctica, because it's Antarctic summer. So we have a red filter to cut out a lot of the blue sky, a lot of light bouncing off the Antarctic bottom. We also, on the other hand, have our actual sensor, which is not commercial off the shelf. We just got this ordered from, I think it's a third-party manufacturer, to Sony, IMX, monochrome, 61 megapixels, super low dark current, super low read noise, exactly what you want for astrophysics. Our actual enclosure, our mechanical engineers were very proud of this. It can withstand 8 Gs, which is ridiculous. That's a 230-pound person standing on it. And we tested this by having people stand on it. And it was good, it worked. But the reason is because that when it comes down, there is a parachute. The balloon will pop and it'll fall. But it has to hopefully, worst case scenario, withstand free fall before the balloon pops up and you hit some ridiculous G-forces on the way down. So hopefully at least the box can handle that. And in terms of our electronics, we're actually using an NVIDIA GPU because we're working with a lot of image data. Image data is big, it's costly, 61 megapixels is a lot. And so just a GPU is the best way to work with it, analyze it, especially on the fly. This is what the inside of AIRIS looks like. I don't have anything else to say, I just think it's cool. Also, I made the animation, so I'm proud of it, I gotta show it off. But yeah, this is the inside of AIRIS. It's missing, thank you. It's missing a lot of in fact, it's missing all of the electronics. It's missing the heat pumps. This was an earlier stage when we had the structure, generally speaking, so you can see the lens components coming out together, you can see the sensor, you can see our motor train down there, you can see the screws, which were a pain to model, but okay, I don't know. In terms of how AIRIS will actually work, AIRIS in action. This is a quick latency budget, meaning time budget from when we first get a signal to what we do right after. So, okay, ADAPT sees a gamma ray burst, right? Pancakes on the moon. What does it do? It builds a likelihood map, right? Basically an area of the sky where it says, oh, it's probably in this direction. And it feeds us that likelihood. We then get that likelihood map. We slew over to where it tells us to look, point at it, and then we watch it, and then we image. And then eventually we analyze some of those images, we stack some of those images, we send those images down the ground, we save them on an onboard SSD, whatever, we deal with those images. But this is the basic pipeline of how it works. Now we gave it about 10 seconds, a 10-second budget to slew and settle. We did overestimate that just a bit. I'll show you guys a video in a second. But just keep that in mind, 10 seconds is what we thought it would take to look from one place to the other. Worst case scenario. Okay, now, we have made a lot of progress on AIRIS. We are in its final kind of stages, and so we have learned a lot. And people say that the best way to learn is by making mistakes. And believe me, we have learned. We have learned quite a bit. I just want to say that, I'm going to go through a quick montage of a couple of things that we have learned, i.e. mistakes we've made. So first off, at some point, the Jetson GPU would only work with one keyboard, not any other keyboard. Any other keyboard would crash it, and the computer that we're working with. Who knows why? We had we wasted too much time trying to troubleshoot it. Had no idea why. We spent 2 weeks trying to troubleshoot the camera, and it turns out that there's just a physical switch that we forgot to, or we missed switching. I don't know. At some point, someone was like, "Oh, I wonder what this does." And clicked it, and everything worked. And so that was 2 weeks of software time just kind of gone. Our Jetson shorted out because a piece of scrap metal was just there. We need to be better at grounding things, but that took us out for about a day. Our chief engineer's car got broken into and stolen. That is not related, but he happened to be working on AIRIS while it happened. And so it was, we were talking on Slack, and we're like, "Hey, how's progress going?" And he just said, "My car got stolen." And so we stopped bothering for the night. But it did turn up. It turned up a couple days later, and all that was missing was, a quarter gallon, or a quarter of the tank of gas, and nothing was gone. And so, thank his lucky stars that things worked out. We also had a little bit of a wire mix-up where, I'm not going to read all this, but this is one of our members getting a little mad because we didn't have vacuum-rated wire right towards the end. And we spent a lot of time. We were sitting, this was around 2 a.m. that he sent this message. People were not too happy, but we forgot to order wire, and it was a bit of a problem. But okay, it's okay. We fixed it. We figured it out. There's one huge horror story that I have to mention. So this is a carrier board. It's something that carries signals from the sensor to the GPU. With no carrier board, no communication, no images, no AIRIS. So it's pretty necessary, right? We find our carrier board. During finals week, I get a call at 1:30 a.m. And I'm in my bed, I'm snuggled up. No, okay, it was finals week, I was studying. And I get a call saying, okay, our live power wire accidentally contacted the frame of AIRIS, I don't know if that happened, and it shorted things out, no idea what happened, we're trying to fix it. And we were like, oh no, right? It's finals week, everyone's about to leave, right? Everyone's about to take off right after the finals finish, so we have to have all hands on deck meeting what's going on. During troubleshooting, we had to do this during our exams. Somehow the fans started smoking. All the parts to overheat the fans are not the ones, right? There's some irony there, right? But finally things worked out. We got things working. I'm skipping over a lot of pain and frustration that I didn't even have to deal with. So I'm happy to skip over it. But as timeline got really pushed out, people stayed over the summer to deal with it. Thank God we used a different kind of board, and things happened to work out. This is what my schedule looked like that day. I had a U-Haul booked for the first 4 hours. I was moving out with my friends who are actually back there, my roommates. We all moved out, got our stuff, packed it, drove away, unpacked. Then I had to run to this final meeting where we figured out what we had to do, and then I had 2 back-to-back finals. And everyone's schedule looked exactly like this. So it was a lot of fun time for any of us. So, okay, there are a lot of lessons learned, and I think that the best thing to take away from engineering lessons are general life lessons, right? Things that you can apply. So, number one, you've got to document everything. Or in other words, capture the moment, right? Don't let it slip away. Tired people will make mistakes. So respect yourself, respect your body, respect your limits. Have secondary flash hardware, which we did not, for a reason amount of it. And so what that means is, you can't put all your eggs in one basket. All electronic work should be grounded, done on a CST mat. And I think that's a good reminder for us. You gotta stay mindful, you gotta stay grounded, and not stress. I find you off your car. Okay, so now that's most of it done. Now I'm going to show you some fun photos of what it actually looks like working on this. This is one of our team members working on AIRIS. As you notice, he's in a bodysuit in the fitting room, looking all snazzy. I don't know who that is because I can't recognize my team members from their eyes. But that is our Canon lens, cost $2,000. That is our sensor, cost $15,000. And so we have to be pretty delicate with them. No dust, nothing like that. And so this is work on that. This is what the inside of AIRIS looked like, kind of stripped away, and this is obviously not what made it, what's going to make it up into the upper atmosphere, but you can see our heat pipes, you can see a lot of our electronics, it's kind of good work. And this is some working on the actual mission, and so we had to wire into the sensor. You can see some circuit boards down there that we had to message into, and so all this was in the clean room, right? Completely wrapped up. I still haven't been in the clean room. I still need to get certified. So I've never been in there. I think only 4 or 5 members of the team are correctly certified to actually deal with this stuff. These are some more photos and videos. That is what AIRIS looks like right now on the far left. You can't see it very well, but there are a list of names of people who have worked on there, as well as some friends, including I think some high school friends who didn't work on the project, but they thought it would be fun to have their name in space. These are some videos. This is us testing AIRIS in a TVAC, a thermal vacuum, just making sure that it can spin and everything. And so TVAC, you suck out, you create a vacuum, and then you cycle through high thermal load, low thermal load, so 40 degrees Celsius, -40, etc. It got to the point where I think we hit -40 and it didn't turn properly, and we were worrying like, oh no, what happened to the wires? Or sorry, what happened to the motors? It turns out that the wires connected to the motor, you'll notice that there are like wires running off of the motor, wires running off of the sensor, had cold welded themselves to the side of the TVAC. And so thankfully that's not a problem we have to deal with up there, but it was a pain to uncold weld what they look like. The next video is, you remember how I said we expected it to take 10 to 12 seconds to slew from one side all the way to the other side, worst case scenario. So we finally tested it, and we're good. We're good actually. So full range of motion, Alt-Az, I think, yeah, that'd be called Alt-Az, and stares right back at you. And of course, on the right side, we have Sophie Fender and Oliver Yeaman. They are our chief physicist and chief mechanical engineer. They went to the Columbia Balloon Science Facility. I think that's how you pronounce, that's how you say it. All the way over in Texas, which is where NASA prepares their missions for balloon integration. And so this is AIRIS. This is the chassis that it is connected to. Adapter is going to sit inside of this chassis, and AIRIS is just sitting right up there on top. Sophie is a senior. Actually, she's already graduated. She'll be heading to Caltech next year to pursue a PhD. Oliver Yeaman is stuck with us for another 2 years. But they put an incredible amount of work into this. They were over at Columbia for a couple of months just this past summer. I mean, we just finished this off, right? I've been adding and subtracting things from this presentation for the better parts of the last 3 months or so, because we've just made a ridiculous amount of progress in this time, including actually integrating it. Okay, then we also decided to have some fun, and we strapped a GoPro to it. You can't see it, the resolution is not amazing, but we are actually going to fly the GoPro. We called it an engineering camera, whatever to get us up there. So it's going to look amazing once it's up there, but we decided we might have just a little bit of fun. Okay. Cool, so what does future work look like for AIRIS? Well, first we have a hang test, that's going to be late July, where they, you guessed it, hang the entire payload, just make sure it connects well to the balloon. It'll be going up later this year, so this December, and then it'll be up there for about a month, so in January. So hopefully, fingers crossed, you see a interesting little paper come out from us about this amazing gamma ray burst that breaks science as we know it around this next January. So we've turned it over to the ADAPT team. It's in good hands in Texas right now. Right now we have outstanding some mission operations work, some software work. Thankfully that we don't need to be there to do it, just based on how are we going to run the mission once it's actually up there, how are we going to communicate with it. Hopefully we'll get a GRB detection, hopefully we'll break ground on some new science, but at the very least it's been an amazing project to work on. And most importantly, we're bringing a lot of our lessons learned to WashU Satellite and the future of the team. Okay, so now what's next for us? Just very quickly, we are working on a couple of future missions. First of all, the keen-eyed among you may have noticed, we call ourselves WashU Satellite, and ADAPT is not a satellite. How dare we? The answer is that we actually are developing satellites. I didn't go over it, I'm happy to. I have a lot of backup slides right after this that I'm happy to talk about. But we're working on a satellite called Scalar, which is effectively a test bed for making sure that we can launch something, making sure it turns on in space, and making sure we can communicate with it, just proving to ourselves that, hey, we can do it. We like to combine that work of space-based architecture with our optical work from AIRIS, with our follow-up work from AIRIS, and combine it into the next level of scalar, which is, of course, vector. And vector is the science of AIRIS in the environment of scalar. And so what that means is we're looking for optical transients, but in space. And so it can be a bit larger, but that is pretty far to the future. First, we need to make sure that these things start working. So in terms of our actual timeline, we've been working on AIRIS and scalar. Now we are hopefully wrapping up on these things. AIRIS will be up around this time, scalar will be launched around this time. And in the intermittents, we have a couple of more projects. The Student Spaceflight Experiment Program is a program run by NASA to create proposals to be flown on the ISS, to create experimental proposals. And in fact, if you participate, you're supposed to put together a bunch of teams of undergrads, and at least one of the proposals will make it on the ISS. So hopefully we'll be doing that about next semester. And for our for Vector, which is a future satellite, we'll be working with this program run by the DoD and Air Force on called the University Manned Satellite Program, and they'll help us work through the entirety of Vector's development, which will be, I graduate around here-ish, so right about here is when it is no longer my problem. But regardless, we found a lot of success in terms of members of our team. They've gone to amazing places over the summers. They've gone to amazing places post-grad, and I'm thankful to work with people like that. We found a lot of success, and we of course bring a lot of the lessons that we learned from working in environments like this to WashU Satellite, because a big part of what we do is giving our team members the abilities to excel in actual spacecraft development in the industry, to work with industry standards, to learn what it's actually like to work in companies. And that's all I have for now. Before I need to thank a good round of people first who really actually deserve the applause. First, of course, Don again, Don and Helen, thank you guys so much for putting this together, and of course ASAM, and of course MSRAL for hosting me. I need to give thanks to Ted Buckley, Mary Sudberg, Matt Fowlerfin, and Molly Allway, and the rest of the ADAPT team for their amazing help with us as we developed AIRIS and integrated and figured stuff out over these last 6 months. I'd like to give a quick shout out to Jeff Gillis and Carmen Rajendra for giving us clean room access, which was invaluable because we have expensive hardware and we need a good place to deal with that. In terms of students, of course, I'd like to thank Oliver and Sophie, who have been doing incredible work with the team. At the same time, Keen Etzger, Andrew Press, Josh Smith, Matthew Dunn, and Andrew Tucker have also been working extremely hard over the summer. No one's paying them, so good for that. Working extremely hard over the summer on AIRIS, and of course the rest of the WashU Satellite team, who have been there for an incredible amount of support. I'm the president, I just get to sit there, look pretty, and give talks. But these guys are the ones putting in the real elbow grease to make the, make the work actually happen. And of course, personally, I'd like to thank first Ben Cook. He was the founder of WashU Satellite. He was the previous president, and he's the reason that I'm standing in front of you today. So I'd like to thank him, of course, for giving me the opportunity to represent WashU Satellite and the amazing things we do. And of course, Santu Dalal, who has been incredibly supportive with me. He's the professor that I work with my exoplanet work. He's actually sitting in the back right there. So thank you very much for helping me over these past few years and for enabling me to give talks like these. And in terms of the institutions, the McDonald Center for Space Sciences, the Physics Department, and the McKelvey School of Engineering at WashU, thank you all very much. Okay, finally, thank you.
Yes, fantastic presentation. On a balloon-based platform, with that fast of a rotating AIRIS, how do you dampen out the torques and angular momentum established from rotating it that rapidly on the balloon-based platform?
That's a good question. That was a concern we had for a while. We wanted to add counterweights. It seems so. ADAPT does have their own damping system, thankfully, and also it's important to notice that we are rotating on right on the center of mass, right? So we try to minimize the torque as much as possible ourselves, and also we weigh 15, 20 pounds. That weighs over a ton, and so there's only so much torque that we're actually placing on Yes.
What flight level are you going up to?
140,000.
100, flight level 140?
That's the figure that I remember. Okay, I think I saw a hand over here. Yes.
Two questions. One is, what is the magnitude limitation of your optical system, and are you using plate solving for either pointing or for detection of these spurious optical gamma ray bursts?
Yeah, so the question was first, what's our limiting magnitude, and second, are we using plate solving? Limiting magnitude, I'm happy to talk to you because I was in charge of that back when I was working on AIRIS. That's the one thing that I know. So we did a full set of like first simulation suites based on our actual CMOS kind of specs, and so we discovered, at a detection SNR of 5, then we go all the way up to a magnitude of around 13 to 14, which is of course best case scenario, right? And there are a lot of other determining factors, and so we'll actually see what it looks like once we're up there. In terms of plate solving, we're using calibration frames and using a whole calibration suite, but no plate solving. I couldn't remember off the top of my head the exact detection method that we're using. I believe it is SFFT, or stochastic fast Fourier transform, and I could not tell you how that works because that was not my job, and it was a lot of math. Okay, yes?
You didn't misunderstand something. Using a lens to pose gamma rays, I thought you needed rays and incidence mirrors.
Oh no, so the gamma ray detector is a separate mission that we are piggyback on. So they will actually determine the gamma ray burst. Oh man, there's a great flowchart that I have of this, like five slides back. So we actually see the gamma ray, when they see the gamma ray burst, they tell us where to point, and then we point our optical telescope to try to find the optics after that.
Thank you. I thought it was a gamma ray.
Oh no, that'd be awesome.
Well, you need a rays and incidence mirror.
Alright, there we go. Yes, in that.
Yeah, so one thing that's really cool about this is like a single mission multimodal.
Yes.
As we've had some speakers talk about, is DAMP, does it notify or interface at all with LIGO?
That's a great question. Actually, I forgot to mention this. Yes, we will be sending these notifications to NASA's GCN, Global Communication Network, which then distributes it to other observatories like LIGO for eventual follow-ups. But of course, there's only so much latency within sending those, and so having a piggyback right there is pretty helpful. Okay, yes?
When you see when the gamma ray is detected, what area of sky do you have to look for?
When we see a gamma ray detected, what area of sky do we have to look for? So that's a good question. It depends on the energy of the gamma ray burst. The general figure that we were given is that that would be able to constrain things such that if they get a 1 mega electron volt watt level of energy per square centimeter level of fluence, they'll be able to constrain that to a 15-degree circle in the sky, which is pretty big, right? 15 degrees, that's a pretty large region of the sky, especially if we're talking about localizing where they are exactly. And so that's why our lens actually has to do with about 10 degrees. So there are some timing algorithms that we have to work through about, okay, what's the strategically best way, minimizing costs, how do we maximize our likelihood of finding something given a certain likelihood function? Because 10 degrees field of view is still not, is not the best we can do, or sorry, does not cover the whole thing. But those are generally the numbers. And then for higher energy gamma ray bursts, we'll be able to constrain it to 5 and 15 degrees. And I don't have the numbers for you off the top of my head, unfortunately. But yeah, generally we do have to have a strategic timing or a timing strategy. Yes.
When you acquire an image, how long does it take for you to transmit that down to someone, and how do you do that?
So our images are huge. First off, they are 61 megapixels, right? And that's just a single image. If we're talking stacking, if we're talking multiple exposures, generally, I wish I had the numbers for you right now. There will be a base in Antarctica that will communicate with, or via Starlink. And but of course, bandwidth is limited, and so we also have a an SSD on board to hold those. but unfortunately I don't have the numbers for you right now. But I'm happy to send some follow-up messages with people that could actually help you later on once I have this. Yes?
Once this mission is completed, where can we find the results? Like what's it published?
That's a great question. Well, hopefully Nature Journal or Nobel Peace Prize. So, it depends how well it goes. But no, at the very least, they'll be available. Likely, we'll put out some papers on just the construction of the mission, especially if it isn't successful. We still got a lot of meaningful results. The negative result is still something meaningful, and so hopefully we'll have it published somewhere. I couldn't tell you where. We had published a paper about it in a internal WashU Journal of Undergrad Research, but generally speaking, we'll try to have it out there. If you're interested in keeping up with WashU Satellite, we do have a website and we have a newsletter that everyone can sign up for at washusatellite.com. The website is still work in progress, but the newsletter is ready for everyone to sign up. So if you're interested in keeping abreast of what's going on, then feel free. And believe me, if we get a detection, you'll be hearing about it. Okay, any other questions?
To McKelvey, and they'll put you on the mailing list, and you'll get the McKelvey magazine every month or every quarter.
Yeah, exactly. McKelvey, the School of Engineering at WashU, also has their own publication. Yes.
Okay, I was going to tell you this in private, but I'll say it in public. Whatever you do in your future career as a scientist, continue with public outreach. You're fantastic.
Okay, thank you so much. Thank you. I feel very grateful to be given opportunities like this. I met Don actually at a bar, which is not as exciting. No, it was an Astro on Tap event, right? It was another opportunity that we had. I presented along with two other members of our team on other missions. One of us presented on Scalar, which was one of our satellites. Sophie actually was the person that presented on Vector, which is our future satellite. But I happened to have the chance to run into Don. He's like, hey, one of your presentations would be fantastic to begin in Israel, and so we decided that AIRIS was the best. As AIRIS was the best that we had, and the most interesting one that we could give. That being said, I have slides on the other ones. But I'm very happy to be given this opportunity, and yeah, I love outreach. I love talking. No, I'm kidding, but I do really enjoy being able to talk to people and being able to share, the amazing things that WashU Satellite and the team is doing. I just can't understate how much, how proud I feel of the team and of the amazing work that everyone else, particularly not me, everyone else has been doing. And I wish I could have them all here, on stage in person. But that thank you slide was the closest thing that you'll be able to get for now. But no, thank you. All right. Anyone else? Any other questions?
Oh, for sure.
Yes.
What type of battery system do you guys use with the temperatures you have to deal with?
It's a good question. So, funny story about the temperatures. It is a nice balmy 25 degrees Celsius up there, which is a little strange until you remember that because there's so little atmosphere, there's very little convection actually pulling heat out of the system. And we're always in the sun, so we always get warmed up. In fact, it's actually a problem to dump heat, which is why we have heat pipes. The good news is that we have a 1-ton metal machine sitting right next to us that we can dump all the heat we want into. So thermals, thermals are always a problem on any space system. It's also somewhat a problem on a near space system. And so, we work on solar power. We work with Adapt. Adapt has huge solar panels. I have a photo of summer here. They have huge solar panels on the side that feed them constant power, and then they give us a little power. Yeah. But actually, the temperature problem, funny enough, just really quickly, is when we're actually on our way up. When we're on our way up, it goes extremely cold, down to, I think, -40, something ridiculous like that. And so we had to make sure that our things lasted until the way up. So we actually thought of turning the system on and having it running and generating heat and warming itself while it was warming up, while it was going up, just in case it would, kill our electronics on the extremely harrowing journey upwards. Yes. Okay.
The guy that blew on the far side over there and tried to get.
Yeah. Oh, I'm so sorry. Yeah. Thank you.
All right, thanks. Yeah, I'm just curious on how robust is the gamma ray detector that you really can show a latency of 25 seconds? That sounds incredibly fast.
Yeah, well, funny enough, the time they take to actually build up the likelihood map is all the way, oh, it's in my pocket, is all the way over here. It's extremely quick. We expect to get the likelihood map within 2 seconds of them receiving of them actually receiving their clone vectors. And so a lot of the electronics on their side are very fast, and then they let us know. So a lot of this time is actually taken up for moving over and taking photos. So thankfully, we don't have to worry about that. Yes.
Did you run any simulations of that?
Of the
Of the process?
simulations in terms of.
I mean, when you get a hit, are you guys that quick with your movement to get it to that part of the sky that quick?
Yes. I mean, that's what I think the other videos are showing is the full range of motion at full speed of the motors. And of course, this is actually part of the simulation suite that we built out to test our optics and to figure out our limiting magnitude for a certain SNR. In terms of response with ADAPT, unfortunately, we hadn't fully tested that suite out. Yes, they're still integrating it in Texas, actually as we speak. But yes, that will be done, of course, in the summer, full testing, and then it'll be ready to send out. Yeah. Okay, next questions. Okay, in the back.
You know, what is the likelihood that the balloon itself obscures you?
Pardon?
What is the likelihood that your balloon obscures your vision?
What is the likelihood the balloon excludes the vision? Pretty high, actually. So, yes, the balloon is huge. We estimate that it'll take up about, they're told us, hey, estimate 45 degrees off your zenith. And that's ridiculous, right? That's a huge chunk of the sky just taken out. So we are also hoping that the gamma ray burst isn't obscured by the balloon. We're hoping it isn't obscured by the Earth's curvature. And we're hoping it isn't close to the sun. Because Antarctic summer, the sun is above the horizon all day, every day, right? It's 6 month-long days. And so it just kind of wobbles around the horizon. And so there's a certain distant elongation from the sun that we have to maintain without burning out the sensor. Luckily, since we are in the upper atmosphere, there is the Rayleigh scattering isn't the worst, so it's not like the daytime sky where you're just completely out of luck for imaging stars. But at the same time, yes, there are a lot of constraints in terms of the field of view that we have for the sky. So here's hoping. Yeah. Okay, next questions. Yes, in the back.
Is this system the one that detected the what they call the brightest of all time?
Oh, the boats. Yes, no, this was, so this is a new system that hasn't been tested yet. Actually, they're just putting it up and demonstrating the tech in the upper atmosphere for the first time this winter. But, the boat of all time, or the brightest of all time, or the boat instead of the greatest of all time, the GOAT. The boat was, I want to say it was either NASA's, one of their gamma ray observatories, or it was BATSI, which is the Burst and Transient Space Experiment, or something like that. But no, it wasn't us. It wasn't us. And that one was ridiculous. That one breaks physics as we know it. I was exaggerating. That one, genuinely, we're not sure how such a thing was produced. But yes, okay. Any other questions? Or am I out of time? Okay, thank you all very much.